All right, let's talk about the different components of a local exhaust ventilation system. We want to focus in this video on the hood or the capture inlet. You can use those terms interchangeably as far as I'm concerned. A ventilation engineer, they might take exception. They might want to differentiate between the two. Before we talk about the hood or capture inlet, let's review the components of a local exhaust ventilation system. We talked about this in the last video, just went over the different components. You got the stack or the exhaust or the outlet, the fan that's moving the air, that gets the air moving, the heart of the system, the air treatment system, not always necessary. You have all of the ductwork, the different plenums and other components that connect all the parts together. Then you have the inlet. This is where the bad stuff gets sucked into the system. Captures contaminants at the source, and that's what we want to focus on. There are different designs, different types, several different designs and types. And some are better for some types of contaminants, some are better for other types of contaminants. Some have advantages and disadvantages and so on. Just, everything has advantages, disadvantages, trade-offs that go along with it. Couple of the types that we'll talk about in here, we'll talk about canopy hoods that sit above the operation to capture contaminants that are lighter than air. These work best with lighter than air contaminants. They have a vapor density less than 1, lighter than air. You'll often see these types of canopies used with flammable liquids, with the rising vapors being sucked up into the canopy, or hot work that's generating the fumes and vapors from the heat, and you have those rising vapors. You'll also see these with what we call dip tanks. Some industrial operations will use dip tanks for cleaning or coating different surfaces, and the dip tanks are usually filled with some type of solvent that gives off fumes and vapors, and the canopy hood will set up above the dip tank and capture the vapors and remove those vapors from the work area as they're created. Again, that's our goal. We want this hood to capture, if possible, everything that's coming off of our point source. Again, point source contaminants are what we're most concerned with. Our hood should be positioned so that it's going to not allow those contaminants to hang around in the workspace. We're getting them sucked out as soon as they develop. We'll also talk about flanged hoods, which a flanged hood is really not a type of a hood. It's a type of hood design. The flanged hoods tend to be generally better, and we'll talk about why they're better. They can create more centerline velocity, which increases the capture capabilities or the capture velocity of your system. But depending on your operation, some operations an open-ended duct may be adequate if that open-ended duct is positioned properly to capture the contaminants as those contaminants are being generated. Generally speaking, our hood needs to be as close to the source as possible. Closer to the source, we're going to have more efficient contaminant removal. And that's where the distance from the source, this is where a lot of the calculations come into play. There are different formulas, different methods that we can use, quantitative methods that we can use to determine what our capture velocity needs to be and how far from the source can we be located and still capture the contaminants. And probably what I'll do for you guys this semester, I will provide the quantitative methods tutorials as optional videos that you can watch. Could be especially helpful if you end up taking the CSP exam down the road, but I'm not going to require you to watch those videos for this class. It will be optional. What I'm going to focus on as far as the material that you're going to be responsible for are the different components and some of the some of the advantages, disadvantages of different systems and material like that. Again, no, I'm not going to, I've thought about it. I'm not going to require you to do any calculations for this unit or any of the remaining units. But you will have, if you're just have a burning desire to learn more about the calculations, the videos will be available to you. The tutorials will be available. Another type of hood is an enclosure hood. Encloses the work process. The contaminated air is removed from the cabinet. We're talking about a cabinet enclosure, generally speaking. Not always a cabinet enclosure. We'll see another type of enclosure hood in the next picture. But the contaminated air, if the work is taking place inside of a cabinet, it's completely enclosed and it's removed from the cabinet and filtered or exhausted to a safe exterior location. Biological cabinets are an example of enclosure hoods. You have biological materials, infectious materials that you're working with, and it's designed to remove and filter or treat those infectious materials without the infectious materials being reaching out into the workspace. And that's what we have here is a biological hood. It's hard to see from this picture, but this is the opening of the biological cabinet. This is a clear glass or clear plastic window that separates most of the worker from inside of the cabinet. The infectious material or other materials that he or she is working with is inside this cabinet. There are fans running that are creating the negative pressure that are capturing any of the infectious materials, not allowing those infectious materials to leave the cabinet. It's a pressurized environment, a negatively pressurized environment that's not allowing material to leave that cabinet. It's really a cool design. If you'd like to read more about biological cabinets, there is an OSHA technical manual on biological cabinets that would provide more detail for you. What we have over here is a glove enclosure. The gloves are built into the cabinet. The gloves stay there. You can see there's a hose clamp that's holding the rubber glove material inside the cabinet. The worker needs to do some sandblasting on a piece or some other work. Maybe they're working with flammable vapors. Whatever they're doing, it's all contained within this hood, and it's never open. It's completely sealed at all times. They can reach their hands inside the gloves and do whatever they need to do. Just like with the biological cabinets, there is a negative pressure that's removing material from the cabinet as the contaminants are generated. This is also a form of a blasting enclosure. Not all blasting enclosures are glove enclosures, but that's what they're doing here. They're using different blasting media to clean or remove rust from a component. But these are examples of enclosure hoods. This is also an enclosure hood. This is a fume extraction enclosure. This is all an enclosure system. Again, not a cabinet, but everything that I'm outlining there, and you can see it goes all the way back. It's probably, I would say, 14 by 14 feet in area, and you've got the one large hood and the one large piece of duct that comes into the hood, and it's sucking out anything that goes on inside of this space. They have polyvinyl chloride curtains hanging down to keep the contaminants from leaving this enclosed area. But this is designed so that workers can enter and work inside. While they're working with whatever materials they need to work with, any contaminants are being removed during the process. These types of enclosures can be designed so that workers could work with some pretty nasty materials without the need for a respirator. As we talk about ventilation design, we're going to be talking about diameter measurement. I need to get that squared away before we go any further, because I'm going to start talking about diameter measurement. Ventilation engineers talk about such things as distance from the source, distance from the fan, and the measurement system they use, it's measured in diameters. What the heck does that mean? When they're measuring in diameters, they're referring to the diameter of the ductwork. A 1.5 diameter distance with a 10-inch duct would be 15 inches. A 3 diameter distance with 10-inch ductwork would be 30 inches. So if we're talking about 2 diameters and it's 8 inches ductwork, 8-inch ductwork, the distance is 2 times 8, 16. Multiply your units in diameter by the dimensions of your ductwork, and that's going to be how the actual distance that we're working with. Receiving hoods captures and contains material ejected toward the hood. They work best when the material is actually being ejected in a direction toward the hood. We see sawdust being ejected from a woodworking tool here. That's an example of where the receiving hood design is going to work best. Grinding operations, grinding produces material moving in a certain direction. Welding, exhaust from engines, wood dust from woodworking machines like we have illustrated here in the photo. If it's a receiving hood, the location needs to be close to the source of the contaminant. Ideally, not more than 1.5 diameters from the source. So if we're dealing with 8-inch ductwork, 1.5 diameters from the source, that would be 12 inches from the source. Your receiving hood should be no more than 12 inches from the source of the contaminant. Now, many tools, many woodworking tools and other tools, they will have an exhaust port or a port where all of the sawdust or other contaminants are leaving the operation. And that's when we can be most effective, when the ductwork is attached directly to the exhaust port on the machine. And I don't know if this is a table saw, probably a table saw there, maybe another type of woodworking machine, but ideally the exhaust or the ventilation system will be designed so the ductwork or the hose will attach directly to that exhaust port on the machine. That's going to be the most effective capture of that contaminant. Here are some other examples of receiving hoods that you might see in an area where welding is taking place. What we have here is a portable system designed for use with welding operations. It's mounted on wheels, on casters. It can be moved around to wherever the welder's working. Up here we have another system or another receiving hood designed for welding operations. It is also a portable system. Looks like that might actually be a Miller unit there. Miller is a big welding manufacturing company, a lot of welding supplies and welding related tools. What we have here would be more of a fixed in place system. We have extraction arms composed of flexible duct that can be adjusted to the work operation, but it is connected to the fixed ductwork. You'll notice the blue flexible duct is connected to the rigid ductwork up above. You can only see it here. You can see this one attached to the rigid ductwork. But the flexibility of the blue section does allow workers to reposition so that they can keep the inlet of the receiving system close to the source of the contaminant, where the contaminant's being generated. Some factors affecting the efficiency of receiving hoods: the hood design. Research has shown that a flanged design is better. The airflow, the volume of airflow in cubic feet per minute. More air, more contaminant capture, pretty commonsensical. Distance from the contaminant also makes sense. Greater the distance from the point source of the contaminant, the less efficient the capture will be. Another thing that's often overlooked, though, these two are commonsensical. This two, there's been a lot of research, or this one up here, there's been a lot of research. This one down here gets overlooked a lot. Cross drafts in the work area or other airflow disturbance can affect the efficiency of capture for receiving hoods. And here's a canopy hood again, a type of receiving hood, normally a fixed hood located above workstation that's generating the contaminant, connected to ductwork. Contaminated air is treated or exhausted from the work area. And here is a couple of examples. We've already seen this picture, and here's another diagram. And this, I believe, this diagram is from the OSHA technical manuals, where I stole that one from. We have contaminants rising from, could be some type of hot work. It could be solvent, vapor from solvents coming from a dip tank, but the canopy hood is right above that, and it's connected to the ductwork. Best for lighter than air contaminants, as I've already mentioned. What we're talking about with a canopy hood is basically the same thing as a range hood that you have in your home. Most newer homes, at least, will have a range hood over the cook stove, but we're talking industrial quality with the canopy hoods versus the really low quality of most range hoods that you see. Even in high-end homes, that you may pay several $1,000s for one, but and they're more pretty than anything else. They're not designed to be industrial ventilation components. Unless you're talking about a commercial kitchen, there are canopy hoods used in commercial kitchens also. Now that's a different animal than what you're going to see in your home kitchen. Even the upscale, the high-end range hoods are not going to be of industrial quality. In many industrial settings where canopy hoods are used, the canopy sets up over the workspace. But there are some work operations where the canopy can't be directly over the workspace. In those circumstances, the side canopy hood is going to be a better option. With the side canopy hood, the hood is actually offset away from the actual work surface or the top of the dip tank, whatever type of operation we're talking about here. When we set the hood back away from the work surface, that allows access to the work surface or to the dip tank or whatever it is from above. Dip tank operations especially, if you're dipping tools or parts into the tank of solvent, you can have it can be very difficult if the hood is directly over the work surface or the tank. So the side canopy hood with the offset hood or the hood away from the work surface is going to be more advantageous. And here's a diagram illustrating what we're talking about. Let me be a little more thorough here. We have the front view and a side view of a side canopy hood setup. We have the work surface here. We have the hood that is set back away from the work surface. And then we have the ductwork that's connected to the hood, and then the fans in the system creating the negative pressure and sucking the contaminants into the system. What else can I say about this? Again, this is the type of setup you may need if you can't have a hood directly over the work area. If a hood over the work area gets in the way, this might be a setup that could work. If you really need a clear, a truly open work surface, then you could go with a lateral canopy setup. With a lateral canopy setup, the hood is actually, no part of the hood is over the work surface. You have the hood, you have the ductwork connected to the fan, other components of the system, and then you have the work surface, the dip tank or other type of work surface here. A lot of times with the lateral canopy hoods, there will be a side baffle or a side wall, and that side baffle is very important as far as controlling the air currents that could disrupt the system's ability to capture the contaminants. It controls those drafts that could interfere with contaminant capture. It's not a fully enclosed hood, but it has some of those same characteristics or same benefits that you have with a fully enclosed, blast cabinet or a biological hood. It's better control for any kind of disruptive air turbulence. As far as the required flow rate calculation, how much airflow do you need for these to be for these setups to be efficient? Here is a formula that could be used. Q is the required flow rate. W is the width of the work surface. L is the length of the surface or the tank. And then V sub C is our desired capture velocity. If we have a specific capture velocity that we're working with, this formula will tell us the required airflow rate that's needed. The previous formula over here, this was for the side canopy hood. If we have a conventional canopy hood where the hood is directly over the work surface, there's a different formula that would be used for that. And one thing about these formulas, you're probably not going to have to use these formulas on a day-to-day basis. If you get to this level of ventilation system engineering, your company should bring in a ventilation engineer or an engineering firm that specializes in ventilation systems. But the value in you knowing this, though, is so that you would be able to converse. You will know a little bit about the math and the components of a ventilation system. You know a little bit about ventilation system design so that you can carry on a conversation with ventilation engineers. So you won't be completely lost in those meetings where they're talking about designing the system. It also, covering the formulas and the math in a class like this also gives you a glimpse of the engineering that's involved and the mathematics that can be involved. Even though you may not on a daily basis use a lot of the calculations that go along with ventilation, some of it shows up on CSP certification exams also. So that's another reason I'm throwing this out here for you. Let's talk about conventional canopy hoods. Again, canopy hood systems must have sufficient flow rate for the removal of contaminants. And the key variables, if it's a conventional canopy hood that's directly over the work surface or the tank, it's tank perimeter or the work surface perimeter, the height of the canopy, and then the desired capture velocity. And I haven't really talked about capture velocity with you. Capture velocity is different than flow rate. They're related, but capture velocity is the velocity of air movement that's required to capture the contaminant into the hood. Capture velocity, the required capture velocity for most contaminants, is going to be in the 100 to 200 feet per minute range. Velocity is measured in feet per minute. Flow rate is measured, it's a volumetric measure, and it's measured in cubic feet per minute. They are related. Capture velocity, flow rate, important when we're talking about ventilation systems. Okay, let's talk a little bit about a flanged inlet versus an inlet that is not flanged. Again, when we talk about flanged hoods or flanged inlets, we're really not talking about a type of hood, but a hood design. On the top here, we have examples of a plain slot hood without a flange, a plain rectangular opening hood without a flange, and a multiple slot hood without a flange. In the lower diagram here, we have the same designs with the addition of a flange. Flanges, generally speaking, are considered to be more efficient. And they're more efficient because the flange reduces turbulence by preventing the hood from drawing air from behind. And I'll show you a diagram that'll make more sense of that here in just a second. Reduces turbulence because it concentrates more air toward the inlet, and the air is not being lost, or the energy of the ventilation system is not being lost back behind the inlet. But again, diagram on the next slide. Now, this reduction in turbulence contributes to an increased centerline velocity, which improves contaminant capture. So flanged hoods, good. Non-flanged hoods, not so good. But you'll still see, non-flanged hoods can still be adequate, but they're not going to be as efficient as a flanged hood. Here we have a diagram of a inlet with no flange, and the air, these lines represent the air movement. We have airflow, desired airflow. We want the air going into at the center line of our ventilation system, of our inlet. But these lines indicate that some of our air without a flange is getting lost back behind the inlet. We're losing efficiency because of the air movement that's going back behind the inlet. That's no flange. Put a flange on it. We have the same diagram here, but we have a flange, and I've highlighted the flange section in red. The flange prevents the air movement energy being lost back behind the inlet opening in this area. Here we're losing energy, losing efficiency. The flange over on the right helps to increase our efficiency. And when I talk about efficiency, the efficiency in capturing the contaminant. Again, flanged, more efficient for point source contaminant capture. A large flange, according to the literature, can increase useful airflow by up to 40%. But engineers who specialize in this, they will spend their whole they may have the specialty that just focuses on flanged versus non-flanged, and they'll have a whole research career caught up in different flange designs. There are different flange designs. We're not going into that detail, but some flange designs are better than other flange designs. But generally speaking, for our purposes, we should just understand that flange is going to be more efficient. A flanged inlet is going to do a better job of capturing our contaminant. We also have different specialty hoods or specialty devices that can be used for different industrial operations. What we have here is referred to as a downdraft table. This is a work table designed with capture inlets in the work surface. In the picture here, you can see all of these little holes. Those are inlets, or those are openings that's sucking the contaminant into the surface of the table. Again, as contaminants are generated, they're sucked into the table. This is a type of device that would work well with a sanding operation. If it was a woodworking shop and there was some finish sanding going on, sanding work that took place on this type of with this type of device, it's going to do a really good job of efficiently capturing the sawdust. It's also good. This type of design can also be really good if we're using solvents or other substances that have a high vapor density. High vapor density, they tend to sink. Low vapor density, they tend to rise. With low vapor density and they rise, we want the canopy hood. With a heavier material, higher vapor density, we want something like this that's going to catch the sinking vapors. The vapors are heavier than normal air and they sink as low as they can. Contain them on a table like this with the inlets in the surface of the table. That's going to be more efficient at capturing high vapor density contaminants. And we've talked about vapor density before, but just as a review, we're talking about the weight of a vapor or gas relative to the weight of ambient air, of normal air. Normal air or ambient air has a vapor density of 1.0. Heavier than air gases are above 1.0. High vapor density are above 1.0. Low vapor density or lighter than air gases are below 1.0. And a great source for this information are your safety data sheets that you should have for pretty much everything that you're using in your work operations. The side baffles also function to control drafts, just like the lateral canopy hoods that we looked at earlier. Another specialty type of capture device is a water curtain, also called a water wash spray booth. Water curtain, water wash spray booth. What we have here, we have an open front enclosure. You see an individual spraying some type of paint or finish on a component, and what we have back here is a curtain of water, water that's capturing the overspray, capturing the contaminants. So you have two things going on here. You have the water curtain that's capturing contaminants, capturing the overspray. You also have conventional air movement or air ventilation systems that are capturing contaminants. With these systems, they can be very efficient at capturing overspray, but you are faced with the dilemma of what to do with the contaminated water. There would need to be additional treatment measures taken to treat the contaminated water. The best water curtain systems, they recirculate the water. They clean the water. They're able to remove the contaminant from the water. They recirculate the water, and the water's not going into the local sewer system. My slide here makes reference to a capture tank. A capture tank, talk to you a little bit more about the capture tank. Capture tanks can be used in other systems, not just in water curtain systems. But a capture tank is part of a system where the liquid and vapor contaminants, liquid and vapor contaminants are collected. The tank captures the liquid components. Normally, even with capture tanks, there's going to be an exhaust hood for removing the vapor contaminants or vaporous contaminants or particulates. Another specialty design that can be useful for some contaminants would be what's referred to as a push-pull system. It's a ventilation system where a stream of air blows over the contaminants or the contaminated air, pushing the contaminated air toward the exhaust inlet. Here we have a slot exhaust. We have an air box that's blowing air across the work surface. It's blowing any contaminated air toward the slot exhaust. As the exhaust inlet is sucking in the contaminated air, the air bar is blowing the contaminated air toward the slot exhaust. You know, it can be a really efficient system. You have the pushing from the air bar. I think I said air box earlier, but the pushing from the air bar and the pulling from the conventional ventilation system. All right, that's a little bit of information about the hood or inlet components of a ventilation system. In the next video, we'll talk more about ductwork and some of the good things to know from a safety professional standpoint when it comes to ductwork. Again, we're not going to be designing these systems. We should be hiring engineers to do this, but it's good to know some of the basics about, again, hoods and ductwork and so on.